Welcome back for another calculus lesson. This is Mr. Thompson. We have moved on to lesson 2-2, graphical and algebraic approaches to the definition of limit. Once again, looking at limits, which should be reviewed. This is pages 34 through 37. Now, first of all, before we get into this, let's look at what the book gives us is the definition of a limit. Now, it gives us a pretty mathematical definition, which is some language that you have to start learning how to read. So we have L equals, and it's written LIM, x to c, f of x, if and only if, for any number epsilon, and epsilon is written as this backwards E. It's a Greek letter. Any number epsilon greater than 0, no matter how small, which means we want it to be small, there is a number and this is another Greek letter, this is delta, a number delta greater than 0, such that if x is within delta units of c, but x does not equal c, and not equal is given to us as an equals with a line through it, then f of x is within epsilon units of L. Now, it's pretty difficult to read the mathematical definition sometimes, so let's just take a look at this line by line. First of all, the way we read this is it is the limit as x approaches c of f of x. That's how we read this. Limit of x approaches c of f of x. Now, it says if we have a number epsilon greater than 0, a number delta greater than 0, we're not plugging in c to x, we're saying x is within delta units of c. So delta is a really small number. Let's say, assume delta is 0.01, or 0.001, 1,000th of a unit away from c. Then we know that f of this x is within epsilon units of L. Well, if we looked at the lesson 2-1, we knew if we were 1/1000th away from the x, then we were 2 1,000ths away from the actual number. Now, this is not the case for all functions. This is just the example that came up before. So that's the definition of limit. Now, it'll be easier to understand the definition of limit if we go ahead and take a look at an example or two. So, let's go ahead and take a look at example number 1, which is on the same page, page 34. So example 1 says state whether the function graphed in figure 2-2a. So I'm going to go ahead and draw that. It's on the next page. Let's see. At 1, 2, it has an open circle. At 5 and 2, it has it's connected. Has something interesting at 3 and 8 and 3 and 10. So this isn't really to scale, but you'll get the point of it. So at 3 and 8, 3 and 10, we have a circle like that, and then the first part of our function looks like this. And then 3 and 8, we also have this little open circle, and then it keeps on going up again. So it's a chopped up function. Now, we want to know if there is a limit at x equals 1, x equals 2, and x equals 3. Now, at x equals 1, we have this little circle here. Now, in lesson 2-1, we saw that that was a removable discontinuity. So yes, we know that there is a limit, and it is 2. So we would write this by saying the limit, oops, that needs to be an L, the limit as x approaches 1 of f of x equals 2. Now, for b, x is 2. Well, there's not even a circle, it's nothing there, so we know the limit is 5. It approaches 5. So we say the limit of f of x as x approaches 2. Notice I read that a little differently, it still means the same thing, equals 5. Now, at 3, we have an interesting situation, because do we say it's 8 or do we say it's 10? Well, problem is we don't know. If you have a situation like this, there is no limit. It is something that we call a step discontinuity. Now, a step discontinuity is different than a removable discontinuity. A removable discontinuity lets us still have a limit. A step discontinuity does not let us have a limit, at least not in the way that we're looking at it. Now, let's go ahead and take a look at another example. I'll go ahead and put it on the same screen, because this one's going to use the calculator mostly. So we have example 4 on page 36. I'm going to separate from the other problem, see if I can get it in here. Now, we have a function, f of x, as let f of x equal 0.2, and then in parentheses, 2 to the x. It is an exponential function. Plot the graph on your grapher. So I'm going to take out my grapher. I'm going to clear it from the last problem, second plus, 7, 1, 2, and then go into my y equals, graph it, so 0.2, point, and in parentheses, 2 to the x. And that's it, so plot the graph on your grapher. Boom. Oh, I guess not boom, something's wrong. Oh, too many parentheses. Now boom. There we go. Looks like what it should look like. So plot the graph on your grapher. A, C calculator. B, find limit as x approaches 3 f of x. Now, let's go ahead and pull up the grapher again. As x approaches 3. Now, in this situation, there's not really much of an issue. All I need to do is plug 3 into my equation. So I can say it's 0.2 times 2 to the 3. So 2 to the 3 is 8 times 0.2 is 1.6. If I look at my table, I should see a 1.6 there. I do, at 3. So that's not an issue. Now, find graphically the maximum value of delta, max delta, you can use for epsilon equals 0.5 at x equals 3. So remember from our definition of a limit, epsilon is our ending value within, how far away our ending value is from the actual, and delta is our input from the actual. So if we want to be within 0.5 away from 1.6, that means we need to be somewhere from 1.1 to 2.1. Now, if we're somewhere from 1.1 to 2.1, then that's not too much of an issue. Graphically, oops, wrong button, there we go. Because it does say find this graphically. Now I'm just going to draw lines at 1.1 and 2.1. So if we want to be within that range, it's somewhere in there. Now, D. Show algebraically that there is a positive value of delta for any epsilon greater than 0, no matter how small. Now, this one gets pretty tricky. I'm going to go ahead and bring up a new screen for this one. So bear with me just a second. It's taking a minute. There we go. All right. So algebraically means we're going to do some algebra. Now I have 0.2. Now, our function is 2 to the x. I want to figure out that there is a positive value of delta for any epsilon. So it's x plus that delta. Remember, the delta is the change in our input, equals 1.6 is what we wanted, plus our epsilon. Epsilon is the range from our output. Now, graphically, how we do this, I'm going to divide both sides by 0.2. I get 2 to the x plus delta equals, now both these sides divided by 0.2. I get 8 plus 5 epsilon. Now, to solve for this, I need to take the log of both sides. So I'm going to have the log of 2 to the x plus delta. I'm going to put that in parentheses so there's no confusion, equals the log of 8 plus 5 epsilon. Moving forward. Now, remember with our properties of the log, the exponent can come outside to the front of the log. So I can say x plus delta on the outside, log of 2. Oops, log of 2 equals log 8 plus 5 epsilon. Now, I just need to solve for my delta, so a couple more steps to divide both sides by log of 2 and then subtract my 3. Sorry, this should have been a 3 the whole time. I messed that up. So I'm going to go ahead and make that apparent. 3, 3, 3, and 3, because it was 3 that gave us the 1.6. Sorry, that was my bad. Alright, let's continue this. So we're going to divide by log of 2 and then subtract 3 from both sides. We get delta equals log 8 plus 5e over log 2 minus 3. Now, this doesn't seem like much of an answer, but it's telling us that we can have a delta for any epsilon. This is a function relating delta to epsilon. I could plug this into a calculator, putting an x there, and it would give me a function mapping it no matter what epsilon is, I can have a delta. So in this situation, it works. That means we can take the limit of it. Now, that's it for the lesson portion of section 2-2. I'm going to go ahead and pick out a couple problems from the problem set of 2-2 and go ahead and put those up.